Um, yeah, I mean, before I even start, I need to go research. Bro, I hate the visual clutter it has. I fucking hate it. Can I close this? I don't want to close this. The amount of visual clutter is like sickening. Uh, O'Reilly. Uh, so we have fuck. Graph. That's why ChatGPT is just like better sometimes. Yes. I get to visually see the book sometimes. That is better. Yeah, the thing about the computer science is it's you can you can learn about a highly specialized field so quickly, so early that it's like puts every other uh, subject to like kind of like shame. You don't, yeah, yeah, yeah. So you don't actually have to have a lot of infrastructure to learn about PhD level of, and you can like actually make things that work straight on, right? So that's like one of the best things about computer science in general is that you can make beautiful things straight out of like with no money in your bank. You can just like research it. It's just like how much are you willing to research, how much papers, scientific papers, if you want to keep up to date. Which I mean, if you're like in an engineering field, especially computer science, you don't actually need to like read scientific papers that much. It's good to like get some ideas from it, I guess, but you actually don't need them. It's kind of overrated because a lot of it is all theoretical, up in the air. It's nothing really like materialized. So it's yeah, I mean, it's what you want at the end of the day. And even some of the scientific research that I'm doing, it's what you want. It's like, what do you want out of this computer? Like, what do you want it to do? And you gotta be kind of honest with yourself too, right? Group. New group. Oh my God, that's the thing. It's like, oh, I mean, you just need to make a lot of money. End of the day, you gotta be like, gotta be like punch people up. Yeah, open relationship. Convolution. Convolution network. RNN transfer graph. Best books on GAN. It's all deep learning too, so it is kind of trip to like read all of this and never even in specific domains in deep learning on graphs. Apply deep learning perspective. Good if you already know CNNs and want to transition. I don't know CNNs. I don't know. More academic but very complete. Fuck it, bro. I'm kind of all over the place. I do need to make an LLM of, bro. I'm spreading myself too thin. Anyways, no. So those are the topics. Adversarial networks. I mean, you'd see even a GNN. I don't know. It kinda is, but it's not. What is RNN? Fucking bitches, bro. I'm better than all of these guys. Anyways. Graphs traversal, pathfinding, subgraph, graph embeddings. Um, yeah, let's just do let's actually start coding. Oh, that's Kafka. Anyways, I'm spreading myself too thin sometimes. I need to come back and combat that. Bye. So, given a 2D grid where one represents land and zero represents water, count and return the number of islands. An island is formed when connecting adjacent lands horizontally or vertically and is surrounded by water. You may assume water is surrounding the grid, i.e., all the edges of water. Fuck it. Uh, so what should I? An island formed by connecting adjacent lands horizontally and vertically and surrounded by water. You may assume water is surrounding the grid, all the edges of water. What should I return? Return the number of islands. So this is one island. Oh, this is one island. Okay. This is one, two, three, four. Bro, how the fuck do you do that? Is there an easy version of this shit? Because what the hell? Okay, let's try it though. Machine learning. I do want to do. I don't like this shit right now. For being honest. Does it? I mean, I think it is kind of useful, but I gotta learn. Anyways, I just want to punch people sometimes. Graph, where is graph? Okay. Island perimeter. How do I? You're given so the perimeter is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What the fuck? The perimeter of this grid. What the fuck? How is it 4? Oh, it's 4. Because that makes sense. How is this 18? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16, 17, 18. 18. We got 18. So how do I figure it out? Um, bro, why is this like this? Makes no sense. How do I figure it out? I don't get it. So I go, so when I see one, how? So I'm iterating over this one, right? Shook, 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 and counting the zeros. Okay, so anytime if it's straight below it, I need to minus one because if there is straight two below it, I need to minus two. Okay, it's getting complicated.
Hey everyone, welcome back and let's write some more neat code today. So today let's solve island perimeter. So this is an easy problem, but I would say it's more of a medium problem in terms of difficulty. It's similar to a different graph problem called number of islands, and you may have solved that problem before. This problem is pretty similar, so we're given a grid, and in this grid we actually only have one island. So you can see this is like the water and this brown piece is the island. So we're guaranteed to have exactly one island. And the only thing we need to do is for this island, we need to find the perimeter, not the area, right? Counting the area would just be counting the number of cells, but we want the perimeter. So for example, this cell.
Okay, if it's one, so we need to stop when it's 0, 0, 0. So that's one argument is when it is 0, 0, 0. We can like stop the loop because it's done. The island is done. So another, okay, I think I can start coding it. The first requirement is uh, while, so I need to iterate over it. I'm sorry. So I need to iterate all over it. And I need to, for every one thing, but I would consider hitting people because I'm a real nigger. How is this a graph? How is this a graph? I don't get it. So when I iterate over it for the first time, it's going to be like, so 1 is equal to 4. One plot of island is equal to 4. When it's something next to it, it's so 4. I need to draw it. So it is 4. 1, 2, 3, 4, 5, 6. It is 8 minus 2. Right. If it is 3, it is 1, 2, 3, 4, 5, 6, 7, 8. So it is 4, 4. So it is 12 minus 4. So what the pattern is. So we're getting a pattern here, which is summation of 4 minus uh, I and I powered 2. Who knows, bro? Who knows? Like a 2I. And I is 0 and I is whatever, right? So that's the, okay. we have a j, and j would be starting at 1. So that's the formula for this one. And what happened when it's an adjacent? So let's say we have 2 and we have 1. So 1, 2, 3, 4, 5, 6, 7, 8. Same. So I need to find the connections. So this and this is equal. Okay. So I need to find the connection and apply this formula. So how do I gonna find the connection? So obvious thing is, so when it is 0, 0, 0, we can end the thing, and so every time we find, so we're going over the, okay, we're going over the first one. We find here, 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 here. We're finding this. How do we do? I don't know. I'm coming to an algorithmic
This
concept.
cell has a perimeter of 3, right? This top, or this left part, this top, and this right part. So let me just redraw it. So, and this center cell, it doesn't actually have a perimeter, right? Because it's not connected to any water. So this cell, we can't really count the perimeter, but take a look at this cell. It has a perimeter of 3, the top, the left, and the bottom, even though the left part is connected to the edge of the entire water, it still counts as a perimeter. So this perimeter is 3. And so what you can basically tell, right, taking a look at this perimeter, we're really just counting the parts that are connected to water, right? Connected to water or connected to the entire boundary, right? Like this part is connected to the boundary, so that counts as a perimeter. And this part has a perimeter of 2, right? The left and the right. Then you move down. This part has a perimeter of 2 as well, the bottom and the right. This part has a perimeter of 3. And when you add all of that together, we get a sum of 16. So that's what our output is going to be. We just want to compute that perimeter and then return it.
Oh wait. So 1, 1, 2, 4, 7. See, we have 7. So j is equal to 7, I is equal to 6. 7 minus 1. Okay, whatever. Whatever. So it's going to be 4 minus 2, I minus 1, 4i, summation, I is equal to 7. So it is going to be 28 minus 12, 60. Bro, I'm a genius. Holy shit. Summation. Bro. So let's take another one, another example. Bro, I'm a genius. Why? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 8. 8 would be, what is that? Like 24? No, 32. 32 minus 14. That would be 18. Bro, genius. Okay, anyways, I got the formula. So for, no, don't do that. I'm, I literally found it. Isn't that crazy? Bro, don't do that. For I in grid, uh, for j in grid, count is equal to 0. If I is equal to the actual element is equal to 1, you just do the entire thing again. And after the count is, we just do the formula, right? Perimeter would be equal to 4 into multiplied 4 multiplied count minus 2 multiplied count minus 1, and I need to return perimeter. Ow! So it goes to the grid, Jung, first one for I in grid, for J in I. So, so what do we have here? We got one, oh, 4 is just a social construct. Okay, so, 1, 2, we have 5. No, it's like You know what I mean? It's not connected. It sometimes can. I need to do another. Okay, this formula is wrong.
To compute that perimeter and then return it. Now, if you've solved pretty much any other graph problem before, you can tell that this problem is going to require a graph algorithm. You can do it with depth first search or breadth first search. I'm going to choose to do depth first search because it's usually more simple. And so that's what I'm going to do. So we're going to do the depth first search algorithm.
I mean, yeah, I need to do a graph problem every day till I get insanely good at it. Start implementing on it. Boom, boom, boom. Is I mean, is graph neural network
You probably saw that
uses?
coming if you've solved the graph problem before. So what are we going to do? Well, we can basically start at any of the cells, right? Let's just start at this cell for convenience, right? What we need to do is we need to visit every single land portion of this graph, right? But that's not enough. We need to somehow find the perimeter of it. How are we going to do that? Well, let's just look at it. So starting here, let's go in all four directions, right? Let's go above, to the right, to the bottom, and to the left and see which one of these neighbors happens to be land as well. So first, let's go up here. This is clearly land, right? So this is one of the other cells of our island. So from here, let's also go in four directions. Let's go to the right, let's go above, let's go to the left, and let's go down here to the bottom, right? But we know we already visited this bottom cell, right? That's where we came from. So we don't need to visit it again. How am I going to keep track of that? Well, I'm going to create a set. You could do an array, and I'm going to call it visit, right? It's going to be a set, and inside of that set, I'm going to keep track of every single position that we visited, right? So the coordinates of this could be I and J, right? So for every position, like this position, I'm going to take the coordinates and put it into our set. So I'm going to do something like this, right? Visit, I'm going to add to it the I and J, the coordinates of all cells that we visited before. That's going to help us when I actually write the code from this cell, right? So from this cell, right? So when we go above, what are we going to find? We're going to find that this is out of bounds. We can't go there, so therefore there's no land over here, right? So since there's no land over here, doesn't that mean that this is technically a boundary? Doesn't that technically mean that this is going to be part of the perimeter, right? Because if there was another cell here that happened to be land, then we could not count this as the perimeter, right? But since there's nothing here, there's no water, there's no land, there's nothing, this counts as a perimeter. So when I make a recursive call up here in our depth first search function, what I'm going to do is I'm going to return 1. I'm going to return 1 because that 1 is going to be added to our total perimeter. So let's keep track of our perimeter. So let's add 1 to it. Right now our perimeter is going to be 1. We just counted this portion. Now let's make a recursive depth first search call to the right. Now I find that this is water. If it was actually land, I would not be able to count this as a perimeter, but there's nothing here. This is water. So I'm going to count this as the perimeter again. So I'm going to add 1 to our perimeter. And the exact same thing clearly is going to happen when we go to the left, right? So since there's nothing here, I'm going to return a 1, add that to our perimeter. So now you may have noticed basically what we're going to be doing is a depth first search visiting every single cell in our island. And once we get to the base case, right? The base case is when we get out of bounds, we reach water or we literally reach the edge of our grid. Then the base case is basically going to be return 1, right? Basically we can add that as part of our perimeter. And then once we've visited every single part of our island, we're going to take that sum for the perimeter and then return it, right? That's all we really need to do. So just to show you a little bit of what's going to happen next is, okay, so we visited that part. Now let's go over to the right over here, right? So in this position, now we're going to do depth first search again. Now we can't go back there because we've already visited. We can go down, right, and up, right? And each of those is going to be the base case. So we're going to return 1 plus 2 plus 3, right? So let's just add a 3. When we go left, the exact same thing is going to happen right from here. In any of the 3 directions we're allowed to move in, we're going to reach the base case. We're going to end up returning 1 for each of them, so we can add 3 to our perimeter again. Now, when we go down here, right, we have 3 directions to move. We can't go back up because that's where we came from. We can go left, which is a base case, right? So add 1 there. There's nothing over here. We go right. That's another base case. We add 1, and we can go down, right? Down is going to continue our depth first search. So really, from this cell, we're going to be adding 2. So let's add 2 left, which is 3 of those is going to reach. Add all of these up. 3 plus. And we are going to need 1 data structure. I'm going to use a set, but you could use a 2D array. I'm going to put this function inside of or of columns. So if either of these are true, then we're out of bounds. There's a few more cases we have to check. So if I is less than 0, we're out of bounds, or if j is less than 0, that means we're also out of bounds of the grid. And the last thing we have to check is if the position we reached is inbound, so we check I and j. And so if this position happens to be equal to 0, that means we reached water. So in this grid, 0 represents water, 1 represents land. So if any of this is true, that means we reached out of bounds or we reached water, which is the base case, right? So, and we know in the base case, we can return 1 because that means we reached the perimeter of our island, right? And there's actually one other base case. So if the position that we reach is in visit, that means we're visiting a part of our island that we already visited before. So that's the base case where we end up returning 0 because we can't, add to our perimeter if we're visiting a island cell that we already visited before. But if neither of these
Okay. Where is body, bro? Fucking
Now,
goat.
this section is about
Fucking goat. Talking like a goat. Walking like a goat.
graphs. So we'll learn various things about graphs. So, but in this video, we will have introduction to the terminology used in graphs. For introducing
Okay, let's do a little overview. Graph neural networks. Amen. Discovering graph neural network. 300 pages. Why are these so long? Social network to introduce data prep. Um, do I need the social network aspect? Spatial temporal GNN. This chapter covers the integration of memory into deep learning models and understanding the difference between models and GNN. Holy shit, bro. Holy shit, bro. Bro. Raw data source. Holy shit. Now we're talking. Now we're getting somewhere. Holy shit. Let's go. Creating graph data models for non-graph data. It is a form of graph data. So yeah, ELT and pre-processing from raw data source, creating data sets and data loaders with PyTorch geometric. What the fuck is? I mean, it's a library. It seems. We provided an overview of graph and graph database. In this chapter, we will delve into the practical aspects of working with graph data as well as non-graph data that can be converted into graph format. This will serve as a prelude of GNN training. We explain some of the consideration involving taking of data from raw state to pre-processed format. This includes turning tabular data into non-graph data into graphs, pre-processing them into graph-based ML packages, thus turning mental models shown in the figure. Mhm. Yeah, we have everything like connects with each other. Yeah, yeah, yeah. We proceed as follows in this section. I mean, does YouTube use graph model? I'm pretty sure they do. We were like, okay, I think they use something like the cosine similarities. But anyways, graph as a social network introduce a project planning brief system covered. Section it discusses the expression of non-graph data as graph using data models. We put these ideas in action 2.3, section 2.3 by taking these data from raw files into pre-processing data ready for training. Finally, ideas of finding graph data provided into okay. In this chapter, we will examine how to create, operate, and a social credit created by a recruiting firm. Nodes are jobs, candidate, and edges represent relationships between jobs and candidates. We will generate the graph data from raw data. In this edge list and adjacent list, we will then use the data in the graph process framework, Network X, and GNN library, PyTorch geometry on the nodes. Wait, so what is PyTorch? Second time. I need to learn all of that. Fuck. Yeah, I need to learn all of
Hello,
that.
everyone, and welcome to a special episode of Code Import.
I need to learn all of that. Anyways, what is PyTorch geometric? Using PyTorch geometry Stanford. Yeah, it is a form of framework. Anyways,
For the first part, I'll just give a brief introduction. Your previous you have option. So once you get the gradient thing that you don't do.
okay, ling ling bing bing. Got it. Is it still used? Is it tight? Is it shit tight, bro? I don't think it is. PyTorch. Fuck. Um. Okay. The nodes in the data include candidates, ID, job, accountant, and industry backing retail. I mean, graph database is like more important, getting more and more relevant. So, yeah, we frame the goal of the candidates on the graph-based challenges, detailing the steps into transforming data into graph learning. Our aim here is to design straightforward data workflow that starts with raw data, converts into graph format, conducts exploratory analysis, and preps it for GNN training in accompanying chapters. In this chapter, we will learn key consideration of planning ML projects involving graphs and GNN, specific significance of creating graph data models, particularly when working with non-graph data. Yeah, kind of makes sense. Necessary steps of processing, pre-processing data for preparation of GNN training. We will be using PyTorch geometry as a package of choice, of course. Anyways, social network to introducing data preparation and planning. Consider a case of hypothetical recruiting of calls and whole staffing various industries, maintaining database for the candidates' profiles, including the history of engagement with the firm and other candidates. Some candidates gets involved with the firm via referrals. Okay. And the whole staff wants most value of database and have they got all these databases. The consultant company scientists helps them. They have few initially questions about the collection of job candidates. Interesting. Some profiles are missing data. Is it possible to fill the missing data without bothering the candidates? History has shown the candidates have been working hard to present future assignment. Does the company's request teams, whole staffing would like to refer groups of candidates who know each other? Is it possible to figure which candidate have worked together in the past if they have non-disclosed information of the past colleagues? Okay, we just need to like find everything about them by triangulating things around them, right? It's like finding the flight MH360 because people were estimating all of this like places that the planes could have went, and people just triangulated and find the middle. People found it. People somewhere in the middle, right? It's similar to that. Like uh, there's a saying which people say, okay, you are the sum of your five people. So what do we do? How do we find who you are? We're just gonna sum sum all of the characteristics of the five people around you and kind of like get where you are mentally. And nowadays, it's who are the five influencers you watch. So it's kind of things are kind of different now. Anyways, some profiles have been missing. History has shown the candidates have worked well in the past together. And so, thus, the company's request teams, whole staffing has tasked you with mining data. Bro, we gotta mine all of this shit and answer the report. And okay, your idea is to take the collection of referrals and convert it into social network where job candidates are nodes and referrals between the colleagues are edges to simply simplify things. So the moves are and the transition of the edges. The moves are the nodes and the transition of the edges. Okay, you know the direction of the referrals and the graph can under. Yeah, it can be unidirectional. In my case, the moves. The yeah. Anyways, that is a different causal graphs thing happening too. So it can be caused either way. But anyways, for this start and the next step, you have defined a data model assembly pipeline can extract and pre-process the data. Before we go further, we briefly touch on the project planning, which motivates our approach in this problem, project objective and scope. Given the problem, clear project objective, requirement, scopes serve as a compass and steering all subsequent action and decision. Every facet of planning the schema creation to tool selection flows follows the core objective, the outline scope. Uh, what the heck? Designing graph data models. Yeah. This is some ETL bullshit. Designing graph data models in machine learning problems involving tabular data, images, text, or a data. Okay, expected way, which implicit and explicit rules. For example, when dealing when dealing with tabular data, drawing data observation, and the columns of features, we can join tables of such data using indexes and keys. If this framework is flexible and relatively unambiguous, we we may quibble about the observation and features to include, but we know where to place them. When we want to express our data with graphs in all of the simplest scenarios, we have several options for what structures to use with graphs. It's not always intuitive where we place entities of interest. It's non-intuitive and ambiguity that drives the need of the system methods. And okay, about the journey of transforming whole staff recruitment data, okay, into graph base. Next, we created the refine ensure the reliability. How do you do it? Okay. So we got understanding data and use case exploring. Okay, design the data model, design your data model schema, sensor models, test the data model, create, test, and validate the test model using an instance of the models and schemas. Refactor schema. Okay. Get with the domain and use case during EDA. I mean, yeah, domain expertise. Designing graph and data models and schema. Now we're talking about designing Bigraph, bro. The fuck is this? Creating instance model. Who used this? I mean, does Instagram? Autoencoders.
There is a library called PyTorch Geometric Temporal, which is an add-on to PyTorch Geometric and provides several recurrent GNN layers. So first I wanted to say a few words about this library. The library offers 3 data structures that can be used to store graphs that change over time. This has efficiency reasons, for example for static graphs with temporal signals. Welcome back to another video about temporal GNNs. This time we will talk about 3 data structures that can be used to store graphs that change over time. This has efficiency reasons, for example for static graphs with temporal signals, it's sufficient to store the graph structure once and only update the node or edge features. The underlying data representation is based on PyTorch Geometric's data object. So if you plan to build your own dataset, you basically need...
So yeah, I mean, it does change though. So I might dynamic graph temporal signal. I mean, dynamic graphs, the graph that change over time. But I don't think the nodes change. I think it's the edges that change. So yeah, dynamic graphs. I mean, do I even need a graph, or is it just? I don't think I need a graph because yeah, I need a graph. I need high quality images, high quality like features.
to build a PyTorch geometric dataset. I've also uploaded a video for that, plus you need to pass it to one of these graph iterators. Another component of the library is a temporal signal split, which can be applied to one of these data iterators. It's a straightforward test-train split that considers the temporal dependence in the data. A third component are several temporal GNN layers that follow the same design patterns as PyTorch Geometric. At this point, there are around 28 different layer types available. Last but not least, the library comes with a couple of datasets that can be used for testing. One of these is a traffic forecasting dataset that we will use for this video. Now let's jump into the code and train some temporal GNN models. So this is the notebook. I've shared the link in the video description. The first step is of course to get PyTorch Geometric, and after that we can install PyTorch Geometric Temporal, which can be achieved by these couple of pip installs. I don't know why, but for me this took quite some time, so you might need to be patient here. In the end of such cells, I typically call clear output to keep the notebook clean. After the installation was successful, we can have a look at the dataset. It is called METRO-LA and contains measurements of information collected by 207 sensors. These measurements take place every 5 minutes and were collected somewhere in 2012 in Los Angeles. This dataset was published with the paper DCRNN, so Diffusion Convolutional Recurrent Neural Network, and it is included in PyTorch Geometric Temporal and can be obtained using this METRO-LA dataset loader. First, we need to instantiate this data loader, and then we call the getDataset function on it. This iterator is a static graph temporal signal iterator because we have a static road network underneath, and the information of each of the sensors changes over time. That's why the second component is temporal, but the first one is static. You might have already seen these arguments num time steps in and num time steps out. In order to fully understand those, we first need to talk about some time series forecasting basics. Handling time series data can be challenging sometimes. There are different ways how you can use temporal data to perform predictions. Let's say we have this sequence of 6 measurements. The most intuitive way to perform predictions is to collect a sequence of past measurements and use it to predict the next time step. In this example, you have a sliding window of size 3, so you always look back 3 time steps and use the information to predict the next one. The labels are highlighted with yellow, and the input features are blue. In our example, so in our dataset, the features and the labels are both the traffic speed. This is a special thing about time series forecasting because the labels will become features for the next time steps. So after the next iteration, we move on with the sliding window, look back 3 time steps, and predict the next one. Of course, the blue inputs can also hold additional information. In our case, it is additionally the time of the day. We can of course also visualize that for our traffic dataset. Let's say these are the speed measurements of a sensor in 5-minute intervals. Then we make a cut at a specific point and ask the model, how will the traffic conditions evolve in the next 5 minutes? Of course, 5 minutes is not really sufficient, and therefore the next possibility is to predict several time steps into the future. Here we would have a total window size of 6, of which 3 measurements are the historical data points, and the other 3 ones are the labels. This would allow us to predict further into the future, in this case 15 minutes. Again, we can also visualize that for a specific sensor, so we use the historical information in order to predict several time steps into the future. I will talk about some more details in a few minutes when we create the model. So I hope this gave you a rough overview on some time series stuff. If you need more information, I can highly recommend TensorFlow's Introduction to Time Series Forecasting, which I will link below. Based on what I've shown right now, these two arguments, num time steps in and num time steps out, should make sense now. They simply mean we use a sequence of 12 samples to predict 12 time steps into the future. And that corresponds to the second example I've just shown. Let's investigate a single data point. We see that the node features X have a shape of 207 times 2 times 12. That means we have 207 sensors, each of them has 2 features, which are speed and time, and we have 12 graphs for each data point, or 12 measurements. Later in our recurrent model, we use these 12 measurements to feed them in as a sequence. On the other hand, we also have 12 labels, and those are 12 time steps into the future, so those are the 12 values we try to predict. These 12 labels are the normalized speed, so under the hood, we perform node regression here. Because the speed labels were normalized, we cannot directly interpret them. However, if you're interested in doing so, the raw data can be found under this link, and further information about the dataset can be found here. I wanted to mention that the shape we encounter here is not always the case. For some of the datasets, you might also need to loop over the data manually. The chickenpox dataset, for instance, consists of individual graphs, and with the argument legs, you can specify how far in the future the labels should reach. Sometimes this is also called offset. So these temporal datasets can be confusing sometimes, and if you get stuck, I can highly recommend to have a closer look into the source code. You can directly see how the features and labels are constructed. Constructed for a dataset. So these are 2 examples from the source code. One is for the chickenpox dataset loader, and the other one for the Metro LA dataset loader. Here you can see, so this would be a classical predict next time step dataset, because as features you use this range, so from I to I plus self.lex, and then one additional index is the target. So you always have this delay to predict the next time step. For Metro LA, we basically have a sequence-to-sequence prediction dataset. That means we have a sequence of observations, and we want to predict a sequence of labels. In our example, we have 12 as num time steps in, as well as 12 as num time steps out. That makes 24 in total, and the first 12 are basically filled with the features, and the remaining 12 are filled with the labels. And here you can see in both cases index is the same variable, which means that the speed labels are basically features for the old observations and labels for the new ones. Let's move on with our dataset. We can of course visualize the target variable. So I take the target y for sensor number 1 because we have 207 sensors, so I visualize the first one, or actually the second one here, and I select a subset of the samples, in this case the first 24 ones. So as this plot shows, there are some trends in the data. It seems that the traffic speed drops very low early in the morning and goes back up at noon. The y-axis is standardized, and the labels can also include negative values here. Next, we perform a simple test train split. This is straightforward this time series problem. In the first step, we take our current node features for the whole graph and the historical information that we've gathered so far. At this point, there is no historical information, so we pass in none. We input both into as many sequence elements we have. In the graph sketch on the get the model prediction. This is typically called autoregressive. Final remark, this also allows to implement stateful models which are able to model long-term dependencies on infinite long sequences. So far, we only had a look at models that had a fixed size historical sequence. The A3-TGCN block that is used in this notebook is designed for single-shot predictions because it does this aggregation over the sequence automatically. By passing in the periods arguments, we can automatically obtain the embedding for the whole sequence. This is quite suitable for
Okay, how does this relate to... Okay, this, I tried it, but I failed at it, but... Pow! 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 Bitches ain't shit, bitch. Ah, nigger, 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 nigger. Network time delay, recursive iterative alien dictionary. Island perimeter and whatnot. It's all in there. Okay. With schemas decided, let's walk through some simple data pipeline from raw data. In this section, we'll assume a project is to create a simple data workflow that will take a data from raw state, perform light exploratory analysis, and end with pre-processed data set that can be used in GNN libraries. Do I even need an ETL. Do I need an ETL? So I get all the data auto somehow and plug them how. So, but yeah. Maximum clone graph wall rotating orange open log course schedule valid graph tree. How does it make sense? Let me over engineer this shit anyways. Uh, Summary of the data pipeline across this section: raw data collection and processing. Collect raw data from various sources such as relational database of files, whatever. I'm going to do the extract, transform, load, extract the data from the source, transform to a specific format that the machines are predetermined. Okay, I need to do some FFmpeg type shit. Data exploration. I don't know how I'm going to do it. How do you do with images? Data exploration on frames, image frames. Convert the process data into formats and compatible with GNN framework like PyTorch and Geometry. Okay, that is pre-processing for GNN. Okay, that is pre-processing. I did get that right. Okay. Please note that while the overall steps can be shown in the consistent with one problem to another, detailed implementation of each test can be unique to the problem, its data, and its stored in there. So, of course, I knew that. The degree of the node is the count of the adjacent node edge encoding mask. In our context, a rank is the first position raw data. The data is unprocessed. Serialization, yes, serialization. Yeah, we need to like serialize into like easily like encode all of that shit. I don't know how I'm gonna do it. Yes, yeah, graph traversals to like find what the best way to like, and yeah, fucking hell, gives me a headache. Raw data often refers to the most unprocessed data, the data such as okay, the starting point could be various sterilized in some way generated. Mhm. It could be a JSON format where keys. I mean, is it? We'll assume a friendly data require queried the log data and industry for both data source sort of engineers and hash product. For this chapter, we'll use the JSON data. We'll assume the recommendation pipe. Okay, we got all of these data. Data encoding and serialization. Considering a workflow is a choice of data format using exploration. Okay, language. Extract. It's what the fuck is this? This is like two, right? Model and data. Fucking hell. We have 033, 045, 131, 141, 122. I think first using the JSON model, we place the data in the file directory, creating an adjacent list. Don't know what it is. Uh, Anyways, creating an edge list, data exploration and visualization. I don't like to do that. The fuck is that? I don't know. Brother, I'm not doing this shit. Nigga, I ain't doing that shit. What the fuck is graph embeddings? Graph embedding, they should understand the graph embeddings and the limitations. This in what is graph embeddings? We're going to discuss how to check chapter 2 in the perform graph embedding. Graph embeddings, a low dimensional representation can be generated for entire graphs and subgraphs, nodes and edges. They are central to graph-based learning and can be generated in many ways. What is GNN used for? Recurrent neural networks. Convolutional neural networks. Okay.
Networks and how they're an extension to traditional neural networks that take. In this video, I'm going to talk about graph convolutional networks and how they're an extension to traditional neural networks that take full advantage of graph structure. When I first got into this topic, I found some of the papers and diagrams a little confusing, but it's actually pretty simple. So if you stick around to the end, I'm confident you'll be able to understand how GCNs work without having to spend hours reading the literature. So first, I'll talk about how GCNs work in general, and then I'll present a content abuse example to really work through it step by step. So if you like this type of content, or you'd like to hear about the live stream journal clubs we do, please subscribe at my website or join us on Discord. A link to both of those will be in the description below. The idea of message passing in a graph is a really powerful concept because a lot of the graph algorithms can be understood from that perspective. In a nutshell, the idea is that a node in a graph can send and receive messages along its connections with its neighbors. This can be thought of as happening in two steps. First, nodes will send out a message about itself to its neighbors, and next, nodes collect the neighbor messages they receive and use them in some way to update itself and understand its environment. In a fraud use case, you might see how known fraud labels can propagate through the graph by continually passing and collecting messages. This is the essence of a label propagation algorithm. Here's a little schematic showing how this works conceptually in a graph that connects accounts with their shared attributes like IP address and credit card numbers. In label propagation, each node in the graph starts with an initial state, and that state is updated by receiving messages from the other nodes that it's connected to. And this repeats the next iteration, except each node now starts with its updated state, which takes its neighbors into consideration. Think of this as smoothing label information across the neighborhood. For deep dive on how this works, check out the first video in the series, which is linked in the description below. GCNs can be understood as a simple message passing algorithm, but whereas label propagation just passes messages about the label value, GCNs do this for an entire vector of input data. So an account doesn't just tell its neighbors, I'm known fraud or not, but my credit card is from the US, and my IP address is from Vietnam, and my billing address is in Ireland, and whatever else you know about the account. If label propagation is label smoothing in a neighborhood, think of GCN as feature smoothing. Let's make this concrete by talking through a simple calculation in a GCN layer. For any node in the graph, first get item aggregation.
I need to like data source all of that. Anyways, that is a graph. It's different too. The way it's used in academia is not the way it's used in. Graph, temporal, yeah, I don't know. Graph-based learning. Recommendations. Yeah, recommending a move could be one case. Drug discovery and molecular. Oh, discovery. Graph specific prediction task is involved. Yeah, I mean, yeah, that's what I was thinking. Like, it can even like predict the next move that is gonna happen, right? If I can predict the next move, I can predict who's gonna win and shit like that. Anyways, we can like, yeah, we can like understanding how graph. Yeah, I mean, if we can predict what's gonna happen, we can kind of graph embedding. I mean, if you do it this way, we can predict the next move. What is good about that? What is good about predicting future? Yeah, what is good about predicting the future, bro? Yeah, brother, I ain't doing all of that, respectfully. Yeah, I mean, graphs definitely gonna look at it. I don't know. I don't know.